this computer. Okay. So hi everyone, this will be a paper review session, the third that I'm doing this semester, so you might be familiar with the format. It will be the same that I'm sharing this paper. I haven't done any slides for it, so we will just go through the paper itself and discuss it like for certain points in detail, other points probably just on the surface. And I think it's fine if you just interrupt me whenever you don't understand anything. So I would be glad to turn it into more like into a discussion than just a presentation. So I think I will get started right away. So this paper's title is Learning Global Transparent Models Consistent with Local Contrastive Explanations. It's by IBM people. I think it was published in the NIPS, which is neural, something with neural. I think it's a great place to publish it. So the main topic is about explainability. And the motivation about explainability, so the one point that is emphasized in this paper is that certain domains like healthcare or finance, they need explanation for black box, for decisions of black box models. And they focus on one special case. So I will later on with the background, we will discuss what kind of explanations exist, but they focus on one certain type, which is that most paper, or a lot of paper, or a lot of methods, they interpret explainability as in a local context, which means for an explanation for specific samples. And one certain way to do this is that the so-called contrastive or counterfactual explanations, which we will see they are like certain like other perturbations of the input, which means like a slightly modified type of the input itself, which results in a different class, or a slightly modified input which still results in the same class. These are the so-called contrast points. So a lot of explanations that exist, they say that, yeah, this is the explanation because look, this other input is like similar in this and that sense, but it's still in the same class, and look, this other input which is differs in this or that feature, and that's why it belongs to another class. So that's local because it explains the whole method on a local level. But there are also global ways to do this, which focus more on the model itself. So like this model decides every time, because that's a kind of a rule, like decision tree. This is that describes the general methods or the general functioning of a model. And one way, which is, so this paper is focusing on, so this purple sentence says that the problem is that global models are good because they explain how the model itself as a big picture work, but they may not be consistent with local explanations. So like that's a big problem of the surrogate models or proxy models. If you try to model a complicated black box model with a simpler one, which simply does not do the same, then it's not a good explanation. So the knowledge gap that this paper addresses is that how to create a global explanation model which is consistent with the local explanations. So that's the red one. That's basically the research question. And they have two main contributions. The first one is actually a pre-step for the second one. First, they created a metric to measure this local consistency. And later on, they use this metric, or based on this metric, they create, or they suggest one way to create a global model which has good local explanations. So they measured local consistency of a model with their local consistency metric and show how their methods is better than the previous methods or other baseline methods. So actually, yeah, they have some convincing results. That's basically the topic of this paper. And let's start with some background or with some introduction. I think I will probably scroll to the background, which is the related work. It's a small section, and this is actually about the background of explanations. So I think most of you already know about this topic. And we had another a seminar or presentation in this NLP seminar. I think the last one or one of the last ones was about the explainability metrics. And for those of you who haven't been here, just to wrap it up, what are the main types of explanations? Actually, I have here another paper open. This is a survey paper. It summarizes quite well the terminology for explanation. So basically, we differ two aspects, whether it's local or global. Another aspect is whether it's post hoc or self-explaining. So what does that mean? Local means that the explanations are for a specific sample, so a specific input data. Like for one sample, for each sample, you can explain why is it that way. And global is when you try to explain the whole model. Post hoc is something that you want to do afterwards. Like you already trained your model, it behaves as it is, and then with a new model or with something with a complete, like sometimes with a complete different model, you try to explain your previous model. So it's something as an afterward action. And self-explaining is something which is encoded in the model itself. So they have some examples here. I'm also like not completely sure what all of these mean, but probably just to, I think all of you have heard about attention. The attention weights, that's something which is local because it's for every sample, and it's self-explaining because it's in the model itself. It's not something done afterward. What's done afterward, they are more like derivative saliences, so something that you want to derive from your model. Or the global post hocs, since they are these simplified models. Like it's something, for example, when you train a black box method, and then based on the inputs and the black box labels, you try to build a decision tree or something which is explainable. That would be a global post hoc method. And global self-explaining, that's probably, I'm not, reinforcement learning is listed here, but for that one, the best example is rule set or a decision tree. So that a decision tree that you trained the original data on, that would be a global self-explaining. Yeah, so this paper is interesting for the topic, but if we go back, we see that they did not list exactly the same categories, but mostly like the local post hoc methods. The one example they mentioned here is what we're also dealing with. This will be this what's it's called here, the contrast points, exactly. The global post hoc methods. So there is this gap that if you create a global method, that's usually not how the model itself works on a local level. The directly interpretable methods, actually this one, the third one, should be the global self-explainable methods, and visualization-based methods is something where you create a feature map or something where you can see which features have the most impact on the output or something like that. So it's not exactly the same categorization, but they also mentioned here in the last paragraph that they concentrate on the local and global post hoc methods. where there is a weak coupling, and they want to improve that. So back to the introduction part, because actually in this part they try to introduce their basic idea or the intuition how they will how they work. Is that I think the first thing we should clarify is this contrastive points, and they have a nice example for that, which is yeah, in this paragraph it starts here. So well, they work with two different perturbations, so it means that small modifications of the input data. And it's really important for the method that the number of features are altered are minimal. So they try to create such contrast points that are minimal in change, so in a minimal distance from the original point, such that, and there are two features, or there are two possibilities. One of them is the pertinent positive, or is called PP later on, and the other one is the pertinent negative, is called PN. The pertinent positive means that it is a perturbation which retains minimal amount of information, such that it is still classified by the model in the same class. So what does that mean? It means basically that if one sample belongs to a specific class, it means that some of the features must be characteristic for that class. So we try to reduce these characteristic features to an extent that it's still classified to this class. And we want to reduce, we want to achieve it in a way that there's a minimal. Well, we will later on define more precisely what this minimal means, but it will be minimal in a certain way. And the other one, the PM, the pertinent negative, is a point which would make it classify into a different class. So it's like the other way around, that you pick another class and the specific features for that class, the features characteristic for that class, and you try to move those features into the direction of the other class, and up until a point that it is actually classified to the other class. And that's what is called a pertinent negative example. So we have actually a numeric example here. So look at the blue one. It's a tabulated data with 3 different features: depth, age, and salary. So if the depth was 30,000, the age was 28, and the salary was 50,000, then the loan was rejected. So that is our original data point. The purple one would be a PP, a pertinent positive, because it is still classified into rejection. But you see that age and salary, they were kept, 27 and 50,000, whereas the depth was reduced to 20. So it's like you would assume that a reason for rejection is a high depth, like 30,000 is high. So you reduce that, and you see that 20,000 is still high enough to classify this sample into this class. So it would be a PP. And the green one would be a PM. They did not repeat the age of 27. And yeah, well, actually here, the salary increasing to 70,000 with the other things being the same. So the depth is 30,000, the age is 27. And you pick another feature, which is more salient for another class, like the salary. You expect that people with a high salary did not get rejected by a loan. So you increase that feature from 50,000 to 70,000, and it's already belonging to another class. In this case, it's a binary classification to the other class. So that would be a pertinent negative. I think it's a clear example to understand this concept of PNs and PPs. They will accompany us for the whole paper, along the whole paper. Yeah. Exactly, and here they already talk about a bit about the call idea. So as I mentioned, they have two contributions. One of them is this metric. So this metric will use these PPs and PNs, and the other one is the model itself. So the basic idea is just on the big picture is that they take these contrast points that they take only this local information. They do not have access to the original points and the original labels, just these contrast points. And they try to create logical conjunctions, which means that it will be an and connection of different terms, mostly like a specific variable is less or equal or greater or equal to a specific value, and they make a conjunction out of it, and that would count as one feature. So that's, in this sense, it is Boolean, or that's the Boolean part of this whole paper. And after that, they have some methods to reduce the number of these conjunction with a discretization scheme. And yeah, but we will see later on because it's not so clear from this introduction. So actually they have some nice pictures, but I came to the conclusion that you cannot really understand it until we haven't seen the details. So I will spare explaining this one and come back later on when we have enough knowledge for that. Let's move on to this third chapter, this third section of preliminaries. So we have to specify some other concepts as well. This base value vector is an important concept, which means that for all the, I think one thing I should mention beforehand is the data they use. So they use quite a simple data, tabular data from this UCI repository. Is it called? Yeah, the UCI repository. So like this magic telescope and whatever. So it's like not textual data or not image data. It's in the future work that they might want to try for a more complex data as well. So we should know that we are dealing with numerical data and it's tabular data, so it's a bit easier to handle. Well, knowing that, what is a base value vector? A base value vector is defined for all the features. So if we have n features, we define a vector of a length of n with base values. And what does a base value mean? A base value, it's basically for each vector, for each feature, a number which is the least interesting. So like it can be user defined, but if it's not user defined, then it's just the median of the value. So they handle, or they analyze the data statistically and take either it is predefined what could be a base value to a certain feature, or they take the median of it. And what is it used for? So in advance, this base vector will be used for, so the idea is that the more the distance from this base vector is for a certain feature, the more characteristic that feature is to belonging to a specific class. Like the idea is you as a data, you won't be classified as a data point. You won't be classified into a specific class if you have values just like the base vector. So if you're like completely average, then you are not characteristic enough to belong to one or the other class. So this would be data points that have like a universal distribution belonging to all of the classes. That's the idea of it. And we'll see how it's used. The upper and lower bounds is just a very simple thing that they define lower and upper bounds for all the features, for statistical reasons and for optimization reasons. And And now here come some terms. The pertinent positive and the pertinent negative features, or what does, it is actually a vector. So we have data points that are vectors as input, and to each of these input vectors, we can create a pertinent positive and a pertinent negative vector of the same length. And it's defined here formally. So I must admit that I'm not 100% sure that I get these formulae, especially because if you count here the brackets, it's something went wrong here. So I guess there's a bracket missing here around max, but like it's already something that disturbs me. And another thing that disturbs me is that this K, it's never defined. So I guess that it's some kind of regulation stuff, but it's strange that it's never written what that is. But anyway, I think what is really interpretable is the text below that. So I would start with that. And later on, you can see that this formula tries to do the same. Yeah, but I'm not 100% sure. So the P of X, so X is an input from our data set. And yeah, let's define this capital C denotes the classification score. So it's a probability, a number between 1 and between 0 and 1. And calligraphic C is just it denotes the classifier itself. I'm not sure if it's used here at all. No, it will be used later. So for pertinent positives, for P of X, what we want to do, let's first read the text. So this is a sparse vector. So a vector of the same length, which the classifier calligraphic C, this is the pre-trained classifier in our case, or it's the black box itself, classifies in the same class as the original input with a high confidence. So if they also want to have this classification with a high confidence, and being sparse, it is expected to have lesser variation from the base values than X. It's in my opinion, it's not so easy to understand at first, but I try to highlight specific elements with specific colors. Like, what does sparse mean? Sparse means that there are a lot of, in a vector, there are a lot of zeros and fairly little non-zeros. How do they do that? So the vector that is the result of this optimization problem is called delta. And what they want to do, or which is one criteria, optimization criteria, is that the zero norm, I hope it's the zero norm. I was trying to find it, what that means. So what I found on the internet was that this like two lines, a term between two lines, and the zero is the L0 norm, which means the number of non-zero elements within the vector. It would actually make sense. It's never written down here what that means, but it would make sense because they're talking about a sparse vector. So if you take the difference of the base vector, so the base vector is the boring vector with the boring values, and if you take the difference to delta and you count the number of non-zeros and you want to keep it under K, it means that your vector will be K sparse, which means that it will have at most K non-zero values. And that's what they want to do, because they want to figure it out which of the features are important for a specific class. So which of the features should have a deviation from the median such that the one sample belongs to a specific class. And that's what is written here, and I highlighted with green. That's the same thing. It says that the variation, that's what I just said, that it has a lesser variation away from the base values than X. So X is a normal data point, but it might have, I don't know, very interesting values. But you want to try out, or you want to figure out which features are the real interesting features. And to guarantee that it has a lesser variation, what you do is see that you try to encase that this, so you want to put these delta features, the features of this delta vector, you want to put it actually between kind of X and the base value. So you want to move these features closer to the boring features, or the specific, you want to move the specific value of a feature closer to the boring features to an extent that it is still classified interclass. You can also move it up until B, and you have to do it in D minus K cases, because you can have at least or at most K non-zero elements. So those are the parts I understood, which is for me a bit more difficult to understand this optimization problem with 2max and another argument on it. So what I think it is about is that you want to try to find a delta vector which classifies to a certain class which is not your class, so another class. You maximize this. I think it's probably important for multi-class classification, multi-label class, multi-class classification in cases where you have more than 2 classes. And after that, you subtract from that the class you actually want to have. So I think that's why it is a minimalization problem, because you definitely want to minimize this one. So you want to have a higher number for the class that you want to have than the class that you don't want to have. And you have certain threshold here, or a kind of like a lower bound for that with this K, which is never explained. Yeah, but I think which is really important is that you want to have this this confidence that this sample is classified to the same class, not to another class. And yeah, you need the argument, not the minimum value. It's similar for the pertinent negative, except for that the bracketing is correct here. So at least that one. The minus K, I still don't know what that means. And the concept is also similar. So it is defined a bit different, in a bit different way. So such that this delta now, it's not the vector itself that we are searching, but a difference, a vector that we add to the original point. And so here we also want to guarantee some minimality, in the sense that we want to change as little, or as we want to change as few coordinates or as few features as possible. So this is the purple one. It's again this L0 norm. So we want to change up to K features of X. And basically we want to do that these coordinates are further away from the base values than those of X. So we pick some of the features, we move them. That's what the green part tells us. We move those deltas. Like if X is greater than the boring value, then we want to have a delta which is also greater. Like we want to move these non-zero values away from the base values in either way. So either more up or more down. That's what the green part says. So these two equations were, or optimization equations, were the formal definitions for pertinent positive and pertinent negative. I think they did not really describe how or what kind of software they took to, there might be a supplement which is not included here, what they took for finding these values, but they always refer this as a local explanation method. So I guess it was something out of the box they took. Yeah, so knowing these basics, the base value vector, these upper and lower bounds, and most specifically the pertinent positive and negative samples, we can move on to the actual contribution, which is two parts. The first of it is this local consistency metric, and the second one is this, the model itself, I would say. Okay, the metric itself is not so complicated, so I try to explain it again with the help of colors. So the basic idea is that we first define a loss function for a specific input, for a specific data point. And after that, we define the consistency metric, which is just basically, it is 1 if it's perfectly consistent, and otherwise it's 1 minus the average loss over the samples. So let's start with the loss function, which is this one here. It's defined as lambda t and b, because I think t means transparent and the b means the black box, I guess. Yeah, denote the black box and transparent classifiers. So the black box classifier is that you have, there is here the calligraphic CB, that's the classifier of a that's a black box classifier, and the other one, the CT, is a transparent classifier, which is built afterwards. That is what we want to build, actually. Yeah. So the basic idea is that we are using this pertinent points, the PPs and the PNs, and there are 3 things we want to make sure. The first of it is the blue one, which means that we want to make sure that for the real input data, the black box and the transparent classifier gives the same output. I think it's something which, it's the most obvious one. But just because they give the same output for the same input on the input data, which was in the training set or the test set, it does not mean that they do the same. So to make sure, or at least to make sure at a certain level, we introduce 2 more conditions. The one is the purple one. It means that if you take this pertinent positive vector, the transparent classifier should give the same value as the black box classifier, and it should also mean that it's this. It should give the same value as the black box classifier gives for the original sample. So that's the whole thing, that the pertinent positive should still be in the same class, even classified by this new transparent classifier. But it should not be the case for the pertinent negatives. So it should not have the same class as for the original input by the black box classifier. I think that's just one thing that they do not say here, that they have to be the same class. So like this just means that if we have, again, not just 2 classes, but 3, it still can be the case apparently here that this the pertinent negative would be, let's say X is class 0, the pertinent negative would be by the black box classifier class 1, and the pertinent negative by the transparent classifier would be class 2, so a different class, but also different from the black box. It would still count, I see. But I think they mostly deal with binary classifications, so that's probably wasn't an issue. So that's basically the loss function. And I think so in that case, if all the 3 equations apply, then you get 0, so there's no loss, and otherwise you get 1. And the local consistency metric for transparent model with respect to the black box model is just summation of the errors and averaging the errors, and that the soil sum subtracted from 1. Obviously, what we want to have is consistent symmetric as high as possible, which the highest value would be 1 in this case. Okay, so we're knowing that. Let's move on to, I just check, but I think it's still too early to, it's too early to understand, yeah, to explain that figure. Okay, the second one would be the real thing, the real model that they come up with. Just a sec. Okay, so now the main idea is, or the key idea as they name it, is that you get k-sparse PPs and PNs. And basically you can define intervals where the values for a specific class should be like within certain boundaries. And you can use these intervals, you can create conjunction of these different intervals and like call it as they call it as a feature. So actually, I have one big question for this whole paper, that if you have these Boolean intervals, then why not use it as a classifier? It's probably not perfect enough, or probably not good at all, because what they do is they create a lot of these intervals and they use them just as features, and as another step, they build another transparent model, a decision tree, up on these Boolean features. But the Boolean features, in my opinion, should already work, but probably they don't, and that's why they do. But maybe I'll return. Do you have a question, Gabor?
Yeah, let me stop you for a moment, because I want to understand what the Boolean features are here, because I think I was getting the intuition up to the point where they define the loss function.
So sorry, I haven't really told yet. I was about to tell what the Boolean features are.
Okay, then maybe, because so that I don't stop you again, let me just check that my understanding so far is, I mean, my intuition is correct, because my understanding is that what this pertinent positive and negative are about is we have who knows how many dimensions for characterizing our input, but we are trying to characterize the model for a given input using 2 vectors. One of them goes really far towards the average, and it still gets the same output. The other one moves really little and still gets a different output. So I guess if our space was like 2-dimensional Euclidean space, then my intuition would be that this is like I'm standing in a clearing, and I don't know where the edges of the clearing are. I don't even know the shape of the clearing. But I managed to find one direction where the woods are really close, and another one where the woods are really far. And that's already a characterization of the shape. And if I get enough of these pairs, eventually I will know more and more about the shape of the clearing. So that's how I can intuitively imagine this, like that. Except what I didn't have is the notion of the average, but I'm talking about a binary classification, like every point in the 2D space is either woods or clearing, and this is more generic because you can have many classes, and also there is a notion of and also you're more interested in that you can calculate an average point, so like something that is most typical, and that direction is actually more relevant than other directions, I guess.
I think you're basically right that like directions, it's more
So my intuition
intervals.
is at best. This was my understanding. And sorry.
I didn't hear you for a sec.
So and I guess the loss function was just saying that we want another classifier to behave similarly with respect to these pertinent ones. So
that's correct.
And this is what they call, I think, local explanations.
The pertinent points are the local explanations, exactly.
And yeah, I guess their original explanation with the depths is better. Like their original examples where you change one thing, except it was a little misleading because in both examples they just changed one thing. But I wanted to have something with vector spaces and continuous space, and that's a discrete space that they used for their examples. But yeah.
What do you mean discrete?
So that their example had a only categorical. No, that's not right.
They were numeric.
The amounts were not.
Yeah. That's very actually numeric. I think you're correct, but with the intervals, I haven't defined yet precisely. So
okay,
I'm about to. So just to continue, the Boolean rules. I'm just looking for the best picture. Because it's probably not so. So let's stick to this equation number 5. It's probably not the best figure to understand it. It's not even a figure, but let's try it. So what we have coordinates of the pertinent positives and coordinates from the pertinent negatives. And I think it's again the text which helps us the most. So for pertinent positives, a specific feature, the pertinent positives say that a specific feature has to have at least the variation of the pertinent positive feature value for it to be classified into a class. So you see that for all the pertinent positive features, you can come up with a clause such that if this pertinent positive feature is greater than the base value, then the feature, or it's called Z in this case, but so then for the data point to be classified into the specific class should be further away. That's what the first says. The second one says that if it's lower, then it should be even less, so further away again. And for negatives, similarly for pertinent negative says that specific feature can have a variation more than X, but not beyond this delta J, because that would mean that it already belongs to a different class. So it's a kind of another way around. If this negative pertinent feature is greater than B, then then Zj should be closer to the base value, so have less variation, and in the other way around as well. This is a big conjunction, and there are certain problems with it. If you see that one problem is that they are intervals open to one end, so they are infinite intervals on a real line, and you see that this equation or this inequality might be true, but very far away from xj, it might not be valid anymore. So somehow we have to also put some upper limits to these intervals, and also because they will use this conjunction as features, they wanted to discretize or to make the number of features discrete, to reduce the number of distinct clauses, and for both purposes, they introduce something like grid points, which means that these values, these pxj and nxj, they cannot be arbitrary, so they are not continuous, but they will be taken from a grid. And we will have pictures for that, and probably it will be time to show you the picture. Just one thing, there's this delta. So what they define is they also define an upper limit, or in this case, a lower limit, which would be the original x value plus a delta. And this delta is a hyperparameter, and it is fine-tuned later on in the algorithm. So I tried to go back to the first figure, if it makes sense. Yes, probably, I hope. So I tried to zoom in this figure. Okay, what we have as input. The yellow ones are the real inputs. Then we have like activation nodes from the neural network, and then we have classification outputs. That's what we have. That's the original model. And then we want to discover the local explanations, or how it's called here is the local explanation discretization. It is on feature level. So it's actually a tedious work, because you have to look at for each sample and each feature. First of all, here for this discretization, as an input, you have for each sample the pertinent positive and the pertinent negative. And after that, you can create these boundaries, and the G here, this GPU, I think, that means that the J refers to the grid point. So it's not the continuous value, it's already discretized by this grid. P means for the positive, U means upper, L means lower, and N means negative. So what basically happens here is that we have an X value for this first feature somewhere. And we have a pertinent positive. We see that the pertinent positive value is closer to the base value. And somewhere we also have a pertinent negative value. And we have specific grid points. The orange one is this, down here is the positive lower, which means that in order to belong to the same class, Z, I think that because if you look at the next step, single data point Z, that's the new point that we want to categorize. So the Z or the Z should describe the general characteristic of the specific class. So Z should be greater than this orange point, is discretized. And that's what also described here in the next one. Can you see my mouse cursor? Just a question, because I'm trying to use this. Can you see, or can't you see?
Yes,
okay.
I can see it.
Okay, great, thanks. So this first term says that for the first feature, Z1, so the first feature should be greater than this, the lower positive grid point, and it should be under the upper positive grid point. And the upper positive grid point, which is the green one, it's the original X plus a delta, which was fine-tuned as a hyperparameter. And that's what it says basically. So the original equation in number 5 equation, it gave us a lower limit, but we bound it. That's what is called here binning and bounding. So we put it into bin and bound it also up, also from the upper part. So that's the criteria that comes from the pertinent positive, but we also have another criteria still for Z. I think this upper one is for the first feature. But so we have a second criteria. which comes from the pertinent negatives. So the pertinent negatives work a bit different. It says that we also have a lower limit, which is the yellow one. So here, which is what is important, that we have the upper limit, the pink one, or this light pink one. It means that it is the most variation that you can have, or the most distant that you can have from the base value. But here we also bound this interval, and we say, but you cannot go arbitrarily low. You can go up until this yellow one, the lower boundary, which is again x minus delta. So this is defined for the first feature, and the same thing is defined for the second feature. They are kind of independent. And the third, and in the third and the fourth cases, there are no terms because the PPs overlap with the base values. And if the PNs overlap with the original points, then also there's no PPs. So they try to reduce the numbers of clauses. They just put in the clauses which are relevant. So, and what will happen afterwards? So just here again in advance. Those clauses or those conjunctions that we get, those are kind of features. As far as I understand, we have one feature for the first, then another one for the second one. And here we've just seen one sample. So then comes the second sample, and the pertinent positives and the pertinent negatives are different for them. So you get new features. Actually, I think you get a lot of features, and that's also one reason why they wanted to discretize these points, because if these conditions are selected from a limited set of values, then the chance that you get the same features are higher. Gabor, do you have a question?
Yes, I'm wondering if I'm keeping track. So the features on the horizontal axis of this figure in the middle, those are the original features of the data, right? So something like in that example, this would be feature 1, 2, 3, 4 would be things like age and salary and that, right? So the original descriptors, the original dimensions. And then I suppose for a pair of pertinent, so we of course have many pairs of pertinent positive. For a given data point, we generate one pertinent positive and one pertinent negative perturbation. So basically additional data points. And then for each feature, we create
at most two intervals.
We create two intervals.
At most.
And it's at most because sometimes the pertinent positives or the pertinent negatives won't give you one, right? Or
yeah.
But when they do, it would be like, I wish they had worked through the example with that, like something like the salary is at least 40,000 and
they have
that is at most 30,000, like something like this.
They have another example here. I have to, they have numbers here. It's probably more understandable, but I have to explain one more thing for that. And then we can look at this example and we can come back to you if it's more clear.
Yeah, but this is the intuition. So this is the very simplified way of putting it. So this is the kind of conjunctions they learn, right? Not learn, but actually generate. And they generate these kinds of conjunctions because essentially a set of conjunctions is a closed rule set not even like a decision tree. It's a rule-based classifier that does satisfy this criteria that it is locally consistent.
But here's a turning point. They don't use these Boolean expressions as a rule set, but they use them as features, and on these features they train another model, a decision tree, to select. A decision tree.
Yeah. Because you would have these conjunctions generated separately for every single data point.
Yeah, and it's way too many. And
I suppose there's also some randomness in how they generate the pertinent positive and the pertinent negative elements, right?
There's not much detail on that. I think there might be a supplementary stuff to explain that more in detail, but they treat that as a black box here.
Okay, but maybe there's no randomness there. If maybe they can perform a heuristic optimization there, but this is still something they would have to do for all kinds of input, and because it's specific to a data point, it's specific to an input, right?
Yeah, it is
pertinent
specific.
Positive and the pertinent negative belongs to a particular input, and this whole process is done for each input and for each feature.
For each feature, there will be an algorithm. Let me just show you. Okay. It will be. But I think I will leave this figure because it's like it's good after you read the whole paper. It makes sense, but until then, not really. And it's the first figure. So let's get back to where we were. The grid points. One thing I wanna explain these grid points because it's easy to understand. So how they create the grid points, it's that they basically they wanna have n bins for each feature, equally distributed, which means that every interval should have an equal probability. So what they do is they do this kernel distribution estimation thing, it's an algorithm which estimates probability distribution function. And what they do is that they always take the k divided by n quantile. So this one picture shows it quite nicely. So they estimate a probability density function and a cumulative density function as well. So, and then they divide it and they just take a look at the quantiles, so that in each of these intervals, the number of samples are the same. So the probability of a value being in one of the quantiles, or one of the bins actually, it's always the same. So here's one example. We have a data distribution for feature one, like this blue one. We see that it's more like it has heavy tail, and the other one, the feature two, it's more like a normal distribution. And we create the bins accordingly. Like you see that for the blue one, the lower quantiles are closer, and for the normal distribution, the quantiles are the closest in the middle. So you got the bins for, in this case, we want to have 7 bins, which means that we have 8 grid points. So you can see the values here. It's quite straightforward. So that's how they create the grid points. And we saw that they map these grid points, and how they map the grid points is described here in this algorithm. Probably I can zoom out a bit because I use colors here again. Okay. So this algorithm describes how the clauses are created and added to the set of F, which is features. Yeah, they call those features. So the output of this, the input of this algorithm is the training set itself. D and the samples, but just the samples, not the labels. Binning matrix G, so G is basically the grid points, the base value vector B, the pertinent positive vectors for all the input and the pertinent negative for all the input, and the skip parameter delta, which just defines, this is just this regularization parameter to fine tune, which is used for the upper limits. So in both cases, that this interval should not be too far away from the original X. Okay, and here's the algorithm itself. We iterate on each training sample, and we also iterate on each feature. So it's a nested loop. It's D times, it's another D, I don't know, J, let's say. So the number of samples times the number of features. That's the number of iterations we do. And in each iteration, at most, we add to, we always add one conjunction, because if you see, there's this Q, and Q, no, so Q is also a big clause. It's a big conjunction, the Q, and one conjunction is for one sample. So it's actually a conjunction for all the features, but for one sample. And when we finished with one sample, we add it to the big set as disjunction. So I think we add it to the set, it will be just a set of features. And this one big conjunction for one sample, it has at most like the number of features times 2 clauses, actually 4, because each clause is a conjunction of 2, but an interval has lower and upper limits. But we saw that it's these pertinent vectors are sparse vectors, so we only consider non-zero values for them. So it's a bit less. But what basically happened, let's take a look at the yellow one, because here's a description for that. Here it will be explained how we use the grid points, because up until now we had the pertinent value and it had to be bigger or lower. But we cannot use the pertinent values because we want to discretize it. I don't know how to pronounce that. Discretize. So we want to make it discrete. And what happens is that instead of this clause, X is greater than P, which says that the feature has to be at least P, we say that the feature has to be at least the grid value below and closest to P. This is this binning, and it should not be too far away from the original point. Therefore, we have this delta, this skip parameter. So this yellow thing describes line number 8, which means that the G is the grid point. And here, this is how we find the grid point for this pertinent positive. So it should be lower, but it should be closest. That's why it's a minimization from the distance. And the S is for the grid point, for the grid point for X. So it's above X, but it's also closest. And yeah, this equation is basically what I try to show here in the first figure. Exactly this one, that we take this orange grid point and not the value where the pertinent value is, but the discrete grid point. And also we cannot take X, but a value X, the grid point closest to X plus delta, and so on. So, oopsie, it's too, hello? Oh, yeah, sorry. Okay, let's move back.
So this whole thing with the grids is really just the
Sorry?
Mechanics of, so we have continuous features, but we put a grid on them so we can do all this. And it's like with those examples of the prices and the salaries and the debts and the age, it's also very intuitive that you don't really need this to be continuous. It's continuous scales, but you're right. Any reasonable
it's an easy thing.
Causalities will just apply.
It's not a difficult thing. It's described fairly long, and this whole algorithm looks fairly complicated, but it's really just about making it discrete. And the other colors are for the other cases, for in case this equation is flipped, and for the pertinent negatives. So I think we don't have to go into details. You get the intuition of this. This part I already explained. This is about the quantiles. It's a small algorithm how they do that, but what's basically happening here is this KDE algorithm, which is generating the quantiles. And the third one, the algorithm, which is this last part is this transparent learner, which is trained upon the features. So here you can see basically the whole procedure. So you have this grid matrix. You get that from the data and from the distribution stuff. And then you use the data set, the black box model, and the black box model to generate these pertinent positives and negatives for every training sample. And using the grid and using these local contrast points, you create this set of Boolean features that we saw above by the algorithm. This is called this big F. And then in the third step, from the original data and from this Boolean feature set, or from these Boolean clauses, you create a binary data set, or they create a binary data set. You see that it's a number of samples times number of clauses dimensional. So it's all the features are either 0 or 1. So you take the input, look at the features, and you put it into the formula, so into this Boolean clause that you learn, and evaluate it whether it's 0 or 1. And you do it for all of them, like for all the features that were derived from the data set. And you get a binary data set, which is not so compact or not so succinct. And in the first step, you feed a transparent learner to this new data set, which is in this case, in their case, was a decision tree. And that's the new classifier. And the idea is that I must admit, I also did not 100% get how this decision tree works. We have some examples. So listing 1, which is here, we see the top 4 Boolean features based on the decision tree. So I'm not, probably you can tell me what does that mean, a top feature of a decision tree? Because I kind of understand how the decision tree always makes the decisions. What is a top feature of a decision tree?
Well, usually
isn't it what is in the top node, like the first split?
Probably it's not written here.
but usually I think it's the one with the highest relative entropy. So basically the one that
that's on the top of the top node.
The top node is the one that has highest Gini coefficient, and that just means it's where you want to. If basically you, after every question of the decision tree, you want to get in every question you want to reduce it's like
it gives you the best classification if you use only this feature.
Yes.
Okay.
Yes. And I'm just wondering, before we look at these examples. So the quantitative evaluation, do they claim that these classifiers will be better than decision trees trained directly on these data sets, or that they will not be worse and they will be more consistent with models that are better?
Yeah, sorry, I skipped that because I wanted to give you an example how the result looks. But let's move back to the qualitative analysis, and after that the quantitative, and after this is actually part of the qualitative. So the quantitative analysis compares their methods to 3 different methods, and we have 2 or actually 4 different metrics. So one thing is this below here. This is a test accuracy. This is the real task, the performance on the task. The other 3 are the consistency metrics, and also divided. The top one is the whole local consistency, which considers both positive and negative pertinent points, and we also have results separately for the positive and for the negative ones. And their claim is not that they have the best test accuracy. They never wanted to have that. They just wanted to have global model which is locally consistent. So global in the sense that you can understand what the model does, and you can, because this decision tree, it gives you features, might be long, but it's interpretable because they are Boolean rules. And how they assure that this model does the same as the original one is that they prove that the local consistency is high. And this test accuracy, I think, is just a matter of fact. By the way, we are not so bad on the real test either.
So what is the standard method?
So okay, I will explain. We have 3 comparisons. The GBFL is their method, this global Boolean feature or something. The standard is decision tree learned on the original data. So original input, original labels, decision tree. You can see that actually for test accuracy, except for the black box, this is the best one, or on most of the data sets, the decision tree. The distillation is decision tree learned on the input data, but not the original labels, but the predicted labels, predicted by the black box. So the distilled one is just a simple global post hoc method that I take the input and output of black box model, and I try to learn a decision tree on that one. So it's a classical global post hoc method.
Yep.
And the augmentation, as far as I understood, because in my opinion, it's also not super clear, the augmentation here, the data is augmented, the original data is augmented with the pertinent positives and the pertinent negatives ones. So in my how I understand that, I also looked into this paper of 15, and I tried to get, so I understood that in a way that this last one is also a decision tree, which had simply more input, like 3 times the input, because for each data input, it also had a pertinent positive and a pertinent negative. What I'm not sure about is that for the original data, did this get the original label or the predicted label? I'm not so sure about that, but probably it doesn't matter.
I think it says that they get it from the black box, using the black box model.
I also understood that way, but it's not so clear to me from this one sentence.
Obtained for each sample of the original data based on the black box model augmented to the original data. I would understand that they only use the predicted label for those where there's no original data, but
okay.
I mean that it makes.
I cannot hear you. or I cannot hear you.
Makes sense,
Yeah,
please,
again.
for a bit, just so we can look.
Sorry, I couldn't hear you for a sec. Can you repeat it?
Can you go back to the table with the numbers and stay there for a bit? Yeah, because I guess for most data sets there is a considerable difference between the standard method and the black box methods. So it really is the case that it was worth in terms of performance, it was worth training something more complex than a decision tree, and then I guess the GBFLs are close to the standard in performance. I'm just looking at the test accuracies now. And they are considerably more consistent with local explanations.
Yeah, that's right. So their claim is that you can see that they dominate on 5 data sets out of 6, or no, 4. So yeah, 5 out of 6, except for magic. And they also dominate by far, but they are just these transparent models. So here, of course, the consistency with the black box would be 1 all the time, or 100%. And so you can see that, like, the double, the result is double as good. It's also, so it's significant by all means. And one other claim is that NA means that this local explanation model was not able to find pertinent negative examples for these data sets. And you can see that in 2 cases it wasn't able to find, but in all the other 4 cases they also dominate by far. So one other claim was that the method is quite consistent with respect to these pertinent negative examples. Yeah. So
now the only question that remains is, do this actually lead to, for some data sets, do this actually leads to rule systems that are visibly better rule systems than the ones directly learned?
Yeah, that's a good question, because they did not compare that one. But I think they did not, that wasn't the purpose, or
I mean that's a qualitative question, because I guess what this means is, I mean, what can a black box model do? And let's stay with these simple examples, like the credit approvals and stuff. So, which is very different than NLP use cases. You have maybe dozens or even hundreds of features, but not more, and that describes everything. And I guess that something that a complex model like a neural network can learn that a decision tree will not are basically latent features. Like, for example, I'm just going to stay with that controversial example that always comes up with explainability. A model is actually racist, and we want to show that it's racist, or we want to make sure it's not. And like, data about credit approval will not have information about the color of the skin, but if a model is sufficiently complex, then it can learn complex correlates, that maybe your zip code plus your income level, and if you want to emulate human decisions, because that's what a machine learning model does, and the humans were racist, then the model can, if it's sufficiently complex, it can learn latent features as functions of other features, right? So I think there was even this was even on the news, that you could show that this would happen. So the model couldn't explicitly learn to be prejudiced against blacks, but because the human decisions were prejudiced, sufficiently complex, it could learn conjunctions of features, like in this zip code with this income level and this age, it's a high likelihood that you are Black. So that could be learned as a conjunction. Now this is, I wonder if one advantage of this method would be that a rule system like a decision tree that it learns would more observably show these things. So that's what I would hope to get from this, that we have a rule system. It's not as high performing, not as accurate as the black box model, but maybe its rules are more indicative of what the complex model is doing.
You mean that these rules,
because I reformulated.
Sorry, sometimes you lag a bit.
Offer a better insight into what the model is actually. Yeah, so are you. So
okay.
I guess we have some connection issues. Yeah, so just as I reformulated something complex as a conjunction of a few simple things, this is what this method is trying to do as well. I'm just wondering if they
Hello. Can you hear Gabor? Can you hear me?
Yes, I can hear you, but not Gabor.
Okay. Gabor is frozen.
So I think it's yeah, on his end.
But if Gabor still can hear us, let me recapitulate. So I think what he told Gabor, oh, no internet. I hope he gets back. So I think what he wanted to do is that these features are so complex that you probably cannot learn directly, but you can learn this way, and that you can realize connection, like complex connections, like yeah, 3 different conditions for being Black, because yeah. Sorry, Gabor, you're back. Can you hear us?
Sorry, I think my connection was gone for.
So basically, you wanted to say that probably this can be an advantage compared to direct rule learning, that these rules are quite complicated, and probably in this way it is easier to learn such complex rules that can also show, for example, a racist condition which in itself it comprises 5 different conditions, like you mentioned, salary, age, whatever, and postal code. And you're one of your, you said that it's probably for directly learning rules, it's probably not so easy or not so.
Actually, I'm what I'm saying is, I guess the point of doing this is to have more interpretable models that more closely resemble the behavior of the complex model. They are not better in terms of performance, but they, in some way, they are more like the complex one. So
if they were better than Sorry, go ahead.
Sorry.
If they were better than the original model, then
I think I'm done.
Yeah, okay, sorry. So I think since it is still a surrogate model, if it were better or as good as the original model, then we wouldn't need the original model anymore, right?
No, sure. But what I'm saying is, it's not even better than what is directly trained on the data. Generally, it's about the same as what they call standard. So they don't have a better performance than what they get from training decision trees directly, but what they do get is somehow the behavior is closer to a black box model.
That was the purpose. They never wanted to get high accuracy. But also one thing. sorry, go ahead.
I was just trying to come up with a scenario where this is valuable, like where we want to uncover and something about what the model is actually doing.
Yeah.
And okay,
this was definitely a scenario for that one. Sorry, I didn't want to interrupt you, but it's so difficult with the lag. I don't know whether you stop or not. And one more thing that they emphasize several times is that regarding the test accuracy is that their method was so this Boolean rules decision tree was trained only on local explanations. So this method did not have access to the original labels. So one possibility, if they wanted to have high text accuracy, or if they wanted to build a really good and explainable model, then they also could have used the original labels. But I think it would be like that would have a different purpose, because the purpose of this model is just to imitate the black box model in an explainable way. And so it doesn't really matter if, I mean, it is matter that the test accuracy is still okay, but it was more important, or more focus was put on that it is consistent on a local level. I'm not sure if it would be a cheat to like train something like their decision tree, but also using the original inputs, because I think that would improve the test results. But that would be probably a different task.
To me, it kind of makes sense that they don't use the label.
Yeah, for me too.
Because what they really want is to emulate the behavior of the black box model. If they were jointly optimizing for also getting good performance, then they would be emulating the black box model a little less.
Yeah.
Yeah. Makes sense to me.
Oops. But I mean, they could have used the predictions of the black box model, and they also didn't use that one.
But they do use it implicitly, right? Because when you generate the pertinence, you are making reference to.
Yeah, in that sense, that's true.
What the model decided.
Yeah. I think one last point is this qualitative evaluation, and that's what I try to show. It's just a small part where they take an example. So, for example, the first they show the top 4 features. So we now know that they are the most, that they have the highest entropy. Is it high? Is the good? So, which rules that separate the best way? And there are certain interesting stuff like this is this magical telescope or sky survey data set. And there are certain features like this redshift, which in all the top 4 features, they always within the same interval. So like 0.8 and 0, so between 0.8 and 0 in all the 4 features. Whereas there's another feature, this RA, which is different in most of the cases, like not all the cases. I think the last 2 are the same, but they have different intervals. So this feature do not make any sense to me, but DERF 1, 2, 3 and plate and whatever they mean. But I can imagine that for data like a loan rejection or acceptance, these features actually make sense, and you can analyze it in a complex way. You can also take a look at the different intervals and discover some connections or hidden biases or whatever. Yes, and there's just some discussion which has remained, but it's just the obvious stuff about that explainability is important and recapitulation. And here's we would also like to experiment on other modalities than tabular, such as images and text. I think it's not so straightforward, not even how to create perturbations for images I can imagine, but for text, like, yeah, we were discussing it yesterday about this stuff of changing words, but as soon as you try or you apply a kind of syntactic or semantic analysis or on the textual data, this perturbation can really go wrong, or like make your system just make that your system cannot cope with them anymore. So I think it's not so trivial to shift this. But do you have any questions? Because I'm at the end now, and it's also over 1.5 hours again.
I asked all my questions.
Yeah, thanks for that. I'm glad if you ask, and also if you ask in between, because that's also feedback for me, whether you can still follow. The others, do you have any questions? I can also stop the recording, so I think.